Futurized goes beneath the trends, tracking the underlying forces of disruption in tech, policy, business models, social dynamics, and the environment. Join me, futurist Trond Arne Undheim, PhD author, investor, and serial entrepreneur, as I discuss the societal impact of deep tech such as AI, blockchain, IoT, nanotech, quantum, robotics, and synthetic biology, and tackle topics such as entrepreneurship, trends, or the future of work. I'm a research scholar in global systemic risk, innovation, and policy at Stanford University. On Futurized, I interview smart people with a soul, founders, authors, executives, and other thought leaders, or even the occasional celebrity. Futurized is a bi-weekly show preparing you to think about how to deal with the next decade's disruption so you can succeed and thrive no matter what happens. Futurized, conversations that matter. If you're new to the show, seek particular topics, or are looking for a great way to tell your friends about the show, we've got the episode categories. Those are at futurized.org/episodes. I am the co-author of Augmented Lean, a human-centric framework for managing frontline operation, and the author of Health Tech, Rebooting Society's Software, Hardware, and Mindset, Future Tech, How to Capture Value from Disruptive Industry Trends, Pandemic Aftermath, How Coronavirus Changes Global Society, The Disruption Games, How to Thrive on Serial Failure, and of Leadership from Below, How the Internet Generation Redefines the Workplace. For an overview, you can go to trondundheim.com/books. At this stage, Futurized is lucky enough to have several sponsors, and to check them out, go to futurized.org/sponsors. If you're interested in sponsoring the podcast or to get an overview of other services provided by me, including how to book me for keynote speeches, please go to futurized.org/store. We'll consider all brands that have demonstrably positive contributions to the future. Before you do anything else, make sure you are subscribed to our newsletter on futurized.org, where you can find hundreds of episodes of conversations that matter to the future. Please also leave a positive review on iTunes. Thanks so much. Let's begin. Ted, welcome. How are you?
I'm fine, thanks.
It's great to have you on the show, Ted. You are a very accomplished researcher in the field of climate. So I wanted to go through some of the experiences that got you there. Math and physics back in University of Toronto. But then you got yourself a PhD on what's called planetary waves at MIT. So I wanted maybe, in a second for you to explain what that's all about, because intuitively it seems very easy. It's a metaphor, planetary waves. Now you are a professor at University of Reading in the UK. You are an expert on climate modeling with a focus on atmospheric circulation, which I guess is no surprise from the PhD. But you've been a lead author on various, climate panel reports and the Meteorological Society. You're also an expert on Bayesian statistics, but I think what we're talking about here is climate storylines, which is something somewhat different. And I'd love to get into that in a second. But why don't we talk about first, just your PhD on planetary waves? It's a very, very interesting principle. I think about it and don't understand it every time I cross, from the east to the west in the US, and people tell me, hey, you're on the jet stream. And for some reason, it goes much faster, going west to east. What are planetary waves in a very simple explanation?
Well, I'll just start with waves. I guess the simplest example of a wave that we think of is just waves on water, on a lake or on ocean. And a wave is a general phenomenon that you get in a fluid system, and air is also a fluid, a gas. It's as well as water. And so in the case of a water wave, you have gravity, which is pushing downward, and then there's always a restoring force pushing back, which is the pressure of the whole system. It's a resistance. And so gravity waves are just the surface gravity waves for water are just oscillations back and forth. And as the water moves up, it wants to move back down again. You have an equilibrium position, which would be still water. And if you push it down, it bounces back up. And if you pull it up, it bounces back down. So every system has these wave properties, and planetary waves are a special case of waves. They're actually known as Rossby waves, is the technical term after a meteorologist, Rossby, and they're a property that you find on any rotating planet. So it requires rotation, and it requires a spherical geometry. So I don't want to get too technical, but the restoring force here has to do with the spin of a fluid. So just as you, the waves always you involve. As you move, you just imagine moving the fluid in one direction and asking whether it gets pushed back or not, and that'll create a wave, this restoring force. And in the atmosphere, we have this spin, and it's a spin about of course, the axis of rotation is between the North and South Pole. And what's important is the orientation of that axis of rotation, which is the spin, and the local vertical. So if you're sitting at the North Pole, it's exactly vertical. But if you're on the equator, then it's at right angle. So you've got no spin at the equator. And it's this contrast between the low latitudes, which have no spin or very low spin, and the high latitudes, which have high spin. So as you move a parcel northward or southward, it gets pushed back by this spin. So it's called vorticity, technically, which is circulation. But it's got the same kind of properties as any sort of wave, if that helps.
But these are massive waves, right? And they interact with other phenomena. So, for example, I grew up in Norway, and I am used to the Gulf Stream. But I am to understand that the Gulf Stream, in principle, is a completely different system. Although it does get
it has
intersect.
Waves too.
Yeah, it has waves too, but it does intersect with these waves. And these are, the waves you're talking about here, right? They are massive. They're not just, these are not some waves on a beach. They're these massive systems, right? Yeah.
Yes. And the motions are sideways. So in some sense, it's basically the motion in the air and the ocean tends to be horizontal. The vertical motion tends to be weak, at least on the large scale. So they're essentially sideways waves. But it's the same principle. If you look at the Gulf Stream in a picture, it's got these meanders, and those are Rossby waves too. The difference is planetary wave is referring, as the name implies, to the planetary scale waves, which tend to be very slow moving. The Rossby waves, which are more like a few thousand kilometers scale, are faster moving, and they're also responsible for the weather systems. So, there's a whole spectrum, but they're all basically Rossby waves. But as they get bigger, they get slower.
Yeah, so just one more thing on that. So in California, they are very concerned about El Nino and La Nina, and currently there's apparently this La Nina pattern, which creates a somewhat colder cycle. So those are all related to this weather system we're talking about here.
This is all planetary. Yeah, so the El Nino patterns basically provide a perturbation which forces these Rossby waves, and these are they're steady, basically time average. So you get these very patterns that will affect a region for a whole season, and depending on where you are in the phase of the wave, it may be warmer or colder temperatures.
Well, we'll get to how this matters or not to climate storylines in a second. But before that, I just want to cover. You shared with me that you're also a little bit of a musician, and in the olden days you played the oboe, and you even thought about going into music. But now you've turned it more into kind of choir singing and other things, and I'm sure you enjoy music on your spare time. What is this relationship, do you think, between analytics and music? Is it just a contrast?
Well, I guess it's sort of a somewhat regularity. I mean, people talk about the motions of the planets, and actually, turns out the planetary orbits, the periods form the intervals, like in music, the third, or fourth, or fifth. So it's because of resonances. So there's something about the universe which wants to resonate at certain frequencies. So maybe that's it. But there's also, this is a rather obscure kind of music, but some of the singing I used to do is called Gregorian chant, and that's actually a very good example of chaos, because you can predict a few notes in advance. It isn't just random, but you can't predict 10 or 20 notes in advance. So it's a bit like the weather. It follows patterns, but they get unpredictable over a long time. So there's a lot of analogs, I think, between music, which has a certain pattern, a certain regularity, but isn't perfectly regular, because it would be boring if it was.
Let's jump to climate storylines for a second, because this is something that you have recently gotten involved with as a concept. And I think you attended a conference, and you guys, came up with this concept. It is somewhat controversial, and it's a concept, I guess, intended to communicate science better, which I'm a big believer in. what is the concept of storylines, and what are you reacting to? What came before storylines? I am to understand that it is slightly related to this idea of how you explain science at the fundamental level. Can you line up the kind of the counterpoint that you were setting up here between storylines and other types of approaches?
Yeah, so I guess you could say that what this is, and it's not just me. I mean, the idea has been around for a long time in various ways. But this workshop that you refer to, we pulled together this concept and saw that it was being used in a variety of ways and tried to generalize it. It's a reaction to, I guess you could say, attempts to be probabilistic, where you try to give some central value with some error bar and stuff like that, which is the sort of a tendency that in a lot of science people want to be. They say quantitative, and what they mean by quantitative is an error bar, some estimate with some uncertainty. Everybody wants uncertainties. Well, there are systems where you can have high degrees of uncertainties that are very quantifiable. I mean, I think casinos understand very well what the margin is, and they can make money reliably because they know the uncertainties. Insurance companies obviously deal with this too. But when you're dealing with climate change, there's a lot of uncertainties that we can't quantify. And fundamentally, the problem is that we have one planet Earth. So all of the statistics that is done, or the classic methods, are all based on the idea of some population. So we would have to imagine a population of different Earths that somehow had evolved in different ways. Well, what does that even mean? We're only on one planet Earth. So, I mean, if I give maybe a prosaic, well, I shouldn't say prosaic, a concrete example, when NASA sent Apollo 11 to the moon, they must have estimated what is the likelihood that these astronauts come back alive. Right. Now, that's not a probability that you can do a whole sequence of runs. There's only one shot. There's one Apollo 11 mission. They have to estimate this, but this is not a frequency. This is not how often it happens out of some hypothetical universe of Apollo 11 shots, right? So this is what's called Bayesian statistics. So that's how you would have to deal with that kind of problem. But it's very difficult, and most people don't really know how to use it properly. So I think it's a reaction against the more blind, or it's called frequentist kind of approaches, where you imagine probability as just something like roll of the dice. So it's a reaction against that, because a lot of there are uncertainties in climate change that are difficult to quantify. So what you do in that case, there is physical understanding, and actually, if you read IPCC reports, for example, it's clear that the physical understanding is absolutely crucial. All the arguments that are made about global warming, it's not made based on statistics, it's based on physics. And so climate scientists have a good understanding of cause and effect. And storylines are ways of building in cause-effect relationships, chains of sequences of events that can lead to certain impacts. You can call it a scenario. That's another way to think about it, except scenario has another meaning in our business. But this idea is sometimes called scenario thinking. So it's trying to appeal to the physical knowledge. Yeah.
So let's hone in on the storyline concept for a second. I do want to get back to these IPCC, the climate scenarios, and the modeling you used there. But so storyline, I think in one of your articles, it was defined as a physically self-consistent unfolding of past events or of plausible future events. So it's both related to modeling the past and modeling the future with causal elements. So it's not like this is the departure. I mean, storyline for some people means complete narrative, as in like complete liberal freedom. But, what you're talking about here is still a storyline within a very distinct causal structure. Yeah, that's what I am to understand.
Language, of course, has many meanings, and we climate scientists we talk about constructing climate information, which we use the term quite casually. But I ran into somebody from a social science background, and they say it's not a construction, because I guess in his community that he was trained in, a construction just means something artificial. So words can have different interpretations for different audiences, and certainly, storyline is absolutely intended to be a cause and effect relationship, but it's not predictive in the sense that you can't say what's going to happen. You can say what might happen, and you try to say if this then that. It's a conditional statement.
Well, let's go to some examples before we go deeper here on these storylines and how they relate to other approaches. So, if you take this Arctic ecosystem collapse from a storm surge, this was a particular example that you cited in the literature. I believe it's Pizarnik in 2011. They were talking about this. Can you talk me through this example? So here we have the Arctic, and I guess we have all read about this melting of the ice around the Arctic, and it's of concern to most people. What is the storyline part of this example?
Okay, right. So the study was done by ecosystem scientists who are field workers, field scientists, and they had studied this ecosystem, and it had been a freshwater ecosystem close to the shore on the Arctic coast in Canada, and they knew it would be in freshwater because there are lake sediments, and they could drill down and they could show that over 1,000 years it had been in this stable freshwater state. But then a storm surge came and inundated it with salt water, and after 10 years it was still salt water, and it was essentially irreversible. So you have for that ecosystem, it's essentially a tipping point. You go from a freshwater system to a saltwater system. So what caused it? It's a storm surge, but normally there would not be a storm surge because there would be ice there. So but the ice had melted. So you have a combination of reduced sea ice cover, which exposed the water, and then a storm. So there's two causal elements there. Now so for sea ice, it's pretty straightforward. We have a strong understanding that the retreat of sea ice in the Arctic has been driven by climate change. There's a little bit of variability around it, of course, but it's clearly an anthropogenic effect, and this has been well attributed. Storms are a random event. There are some arguments that storms are getting worse in the Arctic, and Pizarnik actually claimed that, although I don't believe they really showed any evidence. When we wrote about it, we just said, well, let's not assume that the storm was increased because of climate change, because we don't necessarily have evidence, and we don't need to assume that. We can just regard the storm as a chance event, chaos in the system, but you have this chance event on top of the long-term change. So the narrative is then of long-term change. You could have potentially other causal elements. I mean, sometimes there's coastal erosion, other things. Sometimes a storm surge is caused by the tide being very high. So in Pizarnik, they actually talk about all these different potential factors, and they isolate it down to just a few. So that's the idea. You talk about all the possible explanations, and you look at the evidence that you got, and you try to identify which of them were actually important. But you don't have to necessarily you don't have to decide on this whether the storm was made more intense by climate change or not, because it's not actually necessary. If you were worried about other coastal regions and future risk, you might think about that, but it's not essential. You can leave that open. So part of the storyline approach is leaving certain things open that other readers might bring more to the table. In fact, there was a recent paper published by a colleague of mine and his wife. The colleague's a climate scientist. His wife is a professor of English, and they argued that the part of the power of Shakespeare's plays is that he doesn't specify everything. He leaves certain things open for the director or the audience to interpret. And they argue that actually a key part of storytelling is leaving certain things open. And that's not artificial in science, because we often don't know everything, and we should leave things open.
That's interesting. I guess what they're referring to, there's a literary critic called Walter Iser, I believe, and it's a reader response theory is the literary criticism theory behind that. And so basically the idea is you leave holes, in the text. You leave holes in the narrative for the reader to fill out. And that creative space that gets created is part of the narrative, the efficiency of the narrative. Tell me more about this. So, when you start to write in a more narrative tradition, what does social and other sciences and even natural scientists, what do they think about this? Because when we were talking earlier, you explained to me that in your field, physicists have kind of approached looking at nature almost from kind of two sides. One is, I guess, more the natural history side, and then, well, actually perhaps three. And then you had the statistical paradigm that came in and has kind of had multiple versions. How do you see these different strands, and how do they, I guess, come after each other when you step up and sort of bring out a kind of a new paradigm like a storyline? How does that how does that work in the in the academic structure?
Yeah, so I think the physicists, and I was trained as a physicist, I think are trained to. I mean, the term might be spatiotemporally invariant laws of nature. You're looking for laws that hold everywhere. Of course, they'll be modified depending on where you go. If you go to a different planet, the gravity is different, but the idea is you have the same laws and you can apply them anywhere. So you make very general predictions, but that doesn't that starts to fail you under climate change. Well, if there's uncertainties as there are, especially at the local scale, to do with all kinds of things, either the physics that we can't quite quantify or understand, or even just details like a city or some landscape. Social scientists sometimes don't get the point because they say, well, of course it's all a storyline. So one of the problems I've had, you could say, is that some of the reaction from social sciences, what's the big deal? We know everything is a storyline, but I think they don't quite appreciate how much this general approach and aggregated approach that physicists use is really mainstream. And so for physicists, it is rather radical. But then, of course, there are sciences that are more historical, like natural history, evolution, and so on. I mean, the way that the continents have formed out, we couldn't have predicted that a priori. It's all explainable from physical principles, but there's a chaotic part to it, and so a lot of the world as we have it is contingent on the sequence of events that happen. So that's what a storyline is. It's building in contingencies, and they may be contingencies of the past, or they may be contingencies of the future that we don't know. That's the idea. Mm-hmm. In fact, the term at this workshop, or I guess it was an earlier workshop, actually, a colleague of mine, she's an atmospheric scientist, but she told me about the word storyline, which she said hydrologists use to talk about drought and flood and so on. So I think it just depends on the community, but there definitely are a lot of the more locally focused sciences, for them, it's a very natural approach because it's clear that every landscape will have a different manifestation of the laws.
Well, that's super interesting. So then, what if we go to storylines about the plausible future? Because that's something, well, certainly on this podcast, we explore the future. What are your thoughts on that? Because in climate science, and certainly in the popular imagination of it, and with journalism, there's this notion now of tipping points, which everyone finds pretty fascinating and scary because, here it somehow gets real there's drama because the tipping point, right, is chaos, and it's where you kind of lose control, but also where the paradigm perhaps fails. And whether you're talking about Gulf Stream collapse, which for my Norwegian friends would, I think, be a bit of a calamity, or general ocean warming, which of course is worrisome. And there's sort of 8 to 10 of these tipping points are now really high in the public mind, and it's a bit of a thing. How do you explain tipping points? And you were telling me earlier that tipping points are almost the opposite of a wave. So maybe you can start there.
Okay, if you start almost any physical system, when you write the equations down, you say that the rate of change of some quantity is proportional to the quantity itself. And of course, there's other couplings with other parts of the system, and it's either a positive feedback or a negative feedback. And a wave is a negative feedback. It's got a restoring force. So if you push the water up, it comes back down again, and so on. So a tipping point is an instability, and an instability is just a positive feedback. So as I say, it's if you start to look at equations in physics or in fluid mechanics, basically you get these two classes of behavior, instabilities and waves. Now, a lot of instabilities will will essentially saturate at a fairly small scale. So the weather systems that we have are instabilities of Rossby waves, and they lead to cyclones and anticyclones. But they only have a finite size. They only last so long. they go away, and you can average over the things. The problem with, I guess, the difference with a tipping point is it doesn't saturate, and it will lead to various chain reactions. And the whole system moves into a completely different state. And this is why it's such a different paradigm, because when we think about climate change, most in the atmosphere anyway, we think about averaging over a period of time. I mean, the kind of canonical period people use is 30 years. That's for historical reasons. So you're not talking about a 30-year average. You're talking about all the statistics of all the storms and stuff like that. But you have this idea that climate will be an average over all these different events that you have. It's an average of all the weather systems. But in a tipping point, I guess it might average out over millions of years, but certainly on a human, or even on a human lifetime, even a civilization lifetime, it doesn't average out. So you're basically sent on one pathway. It's called a bifurcation in mathematics, but you don't. It's not a spatial. You can't average over everything that's possible. You get stuck in a certain state. So it's a combination of this instability and then irreversibility that is the hallmark of a tipping point.
Well, the way you explain it here, it doesn't sound terribly easy to do science on a tipping point, or at least predicting.
Well, there are simple systems like some of the ones that you talked about. Of course, one of the reasons that we believe in tipping points is we can see them in the paleoclimate record, and there's definitely very strong, very clear evidence of these oscillations that have nothing to do with any known forcing, like orbital forcings. They have internal timescales. And they're these oscillations that can change the whole climate for hundreds of years, at least in a certain region, like the North Atlantic is a classic of that, because the Greenland ice core has told us all kinds of things about this. And a lot of scientists do have rather simple mathematical models of these kinds of behavior to do with the ocean circulation. When I say simple, they're just idealized to a few basic feedback processes. So the fact that you get this kind of behavior is actually not surprising at all. If you study what's called nonlinear physics, and this just arises in all kinds of systems, it's actually more the rule rather than the exception. It's more difficult if you talk about things like ice sheet collapse, because that involves a lot of detailed processes, and as far as I'm aware, there aren't really accepted general models of those properties. But for the ocean, it's the possibility is not at all surprising, and people have been working on this for decades, at least in theoretical models.
All right, so lots of issues here: ocean warming, ice sheet collapse. Let's stop a little bit around these IPCC scenarios, because I just want to be honest. I have read some of that work. I respect it. There's a Nobel Prize involved. We all know that the future of the planet is in the mix here. And there is a notion of storylines in there. There are also some socioeconomic scenarios. There's certainly the word scenarios appears many times. And I'm a bit of a scenario expert in futurist tradition, but I have to say I get lost in these scenarios. It's very complicated. I find them hard to read. And so I'd like you to just explain how did all these things get constructed in the way that they are, and what is it that an IPCC kind of scientist sees? Where is the value in sort of writing such a complicated set of documents to describe? Obviously, it's a complicated process. Maybe the answer is just that.
Well, I'm not an expert in the in IPCC. There's a fairly clear distinction between what would be called the it's now called a shared socioeconomic pathway, but SSP. But it's a scenario of how the world's going to unfold. Do we all cooperate? Are we at war with each other? Are we going to burn fossil fuels forever? Are we going to move to a green economy? So it's got these various, you could say, visions of what the future might be. Some of them are dystopian and some are utopian. They have a storyline behind them. They use that word. What they mean, again, is self-consistent. So you don't assume that we're all going to be environmentalists and at war with each other. Those don't seem like things that go 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 together. So there's a self consistency in the worlds that are imagined, and then sorry, can you? I'm getting a alert, but maybe it's still okay.
Yeah, no worries. There are some alerts here and there.
Right. If my connection, it seems to be fine. Okay, sorry. So in you imagine a scenario. Well, a storyline is a narrative of a future world, which is supposed to be self consistent, and then people quantify what they call a scenario. Then is what that actually means in terms of population and things like that. It goes back to there's the famous study of the limits to growth in the 70s, where you can develop a system model and you try to map out how these things might unfold. They're not predictions; they're just possible scenarios. A criticism of it is that they're very global. They assume the world all behaves the same way, which is not very realistic. But anyway, that's what it is. Now, you might argue, why do we have it so complicated? I don't really quite know. I guess, everybody in any particular field, people will say that I'm trying to make atmospheric dynamics too complicated, and I'll say that you always find that someone else's work is too complicated and your own is oversimplified. That's just the way we think, I think. I do think there is a sense to try to make it maybe overly rigorous, and that's where a lot of the quantification comes in. And so there's a lot of work on fine-tuning, overshoot, and all these things. I don't know. I mean, I don't get too personally motivated by that, because it seems to me that we aren't going to tune climate. That's not how things are working, but that's just my own view. But for example, a way to simplify things is, rather than which the UNFCCC, the UN Framework Convention on Climate Change, has done in the Paris Agreement. It talked about 2-degree worlds, 1.5-degree worlds. That really simplifies things. So rather than imagining a certain pathway, you just say, what is it going to be like if we're in a 2-degree world? And then you can imagine different different populations, different structures, and you're free to imagine that maybe Europe goes one way and U.S. goes another way, which is certainly possible. So it gives you a lot of freedom. So I think it could be a lot simpler, actually. And I don't quite understand. I think there's just a feeling we want to put error bars and everything. So when you look at these IPCC reports, they're trying to be very quantitative. But ultimately, there's a lot of uncertainties, and I think we would do better if we just had simpler storylines that are physically self-consistent, and then people can create their own storylines at a local scale, because what happens in a certain region could go in a different direction than the overall world. I mean, we're all in the same climate, but in terms of the social conditions, that could be very, very different. Yeah. But I think, partly it's just human nature. The IPCC reports have just been getting longer and longer and longer. I mean, a colleague of mine plotted the number of pages, and it was just a linear. We definitely need IPCC, but I'm not sure that we need it to be quite so big. And I think I would wish that we could still have, global statements that are endorsed by the UN, but I think we should put more effort maybe at the national or regional or local scale.
Mm-hmm. We talked about the ice sheet collapse a moment ago, and you said, well, that is one tipping point that perhaps has had a different sort of set of data connected with it, and that's because the way that you would measure this is more in the natural history type of things. They're more like point measurements of the ice itself, or not. I
think I could get something wrong, and forgive me if I do. But as I said, we do have quite good records of the manifestations of these oscillations in the ocean, from combinations of ice cores over land that give you the time series of various climate proxies and things, as well as the sediments in the ocean. When it comes to ice sheets, though, it's the record that's important is what's happening between the ice and the land. And of course, the ice is eroding that at the same time. So I don't think there's long-term records of the process itself. So, scientists are making field measurements each season, trying to see how things are happening. So that's a case where the process is at quite small scales, maybe, hundreds of meters, are actually determining what's happening on a thousands of kilometer scale, which is a bit scary too in terms of our ability to actually quantify that. So,
Mm-hmm.
but they all begin with there are physical models. I don't mean to imply that they aren't, but how to make them really quantitative to apply to the system as a whole is challenging. There is a lot of work on this, of course,
Mm-hmm.
but ultimately it's just instabilities that lead to systems getting out of control.
You told me earlier, which I really am reflecting on, that you're actually a bit more worried about the social tipping points than about the physical tipping points. Can you explain that a bit?
Well, I guess, I'm certainly no expert on the social side, but just my interest is at the local scale of climate change, and at the local scale, you're dealing with droughts and potentially food security problems and migration problems and stuff like that. Areas becoming unlivable because of sea level rise. So and it's easy to see that just that societies are actually somewhat fragile. I think we saw that, COVID has mixed lessons. In some respects, the societies were rather resilient, like supply chains for food, for example. Once all the toilet paper had been brought back in, but on the other hand, other things are not, and there are these cascading impacts that you can have with the global supply chains, with ships getting caught, not being able to unload and this sort of thing. There's, of course, financial. I mean, Britain just had this huge hole in the budget. The government didn't even do anything. They just said they would do something. And all of a sudden, Britain has been set maybe 5 years back in terms of its economic planning. So there's these huge shocks that can happen either through finance or through food or all these chains that happen around the world. So that's what I'm just the kind of tipping points that physically the people are looking at are 100 years or more off. In fact, for sea level rise, even if the ice sheets on Antarctica or Greenland start to collapse, we're talking about not for a few hundred years to really get serious amounts of sea level rise. But I think within decades, we could have a lot of social problems, because it's not just climate change, of course; it's all sorts of other biodiversity and other things. And of course, the gap between rich and poor is growing, and that's going to lead to some sort of a crisis, I'm sure. And of course, climate change just aggravates that as well. So I think that's why it's partly because I'm interested in the local rather than the global scale. That's just my own scientific interest, but also at the local scale, you very much get into these social contexts, and I think society doesn't seem very very stabilizing to me at the moment. So it's a bit of a worry how all this might go.
Well, so let's talk about the future a bit. What do you think is likely to happen? I mean, there's two questions I have for you. I mean, one is more narrow, and is we've been talking about storylines and to what degree they are incorporated in the scientific modeling of the future in your field, in climate science generally, or in other fields. First, let's handle that narrow question first. I mean, are you confident that the response, which seems significant to your work there, do you think that there's a new thrust of researchers that are starting to think more consciously about the fact that what they should be doing perhaps has to at least resemble somewhat of a story, and that there's a point there? So what has the response been?
Yeah, absolutely. And I mean, one of the pieces of evidence that I use for that is in the last IPCC report, the sixth assessment report. There's a discussion of storylines, and there's a box on it, and there's a glossary term. And actually, it's been a very helpful concept for the IPCC, because there was a tendency to focus on what was likely to happen, and a lot of statements about this will happen with big uncertainties. But the governments wanted treatment. It is meant to serve governments, after all, and the governments wanted treatment of what they would call low likelihood, high impact events, including tipping points. So you can't talk about tipping points without a storyline. So actually, it was already being used. People were talking about sea level rise. They would talk about high level sea level rise scenarios, and these are actually storylines too. So it works at both for the global scale and for the local scale. And so it's growing. I just see more and more interest. I mean, I work with even some private sector with water company in England and like that, and they because they're concerned about drought. It's very hard to put probabilities in drought because every drought is a bit different. They don't it's hard to characterize them with a single number. You have to take a more of a narrative approach, and so I can just see in many ways it is becoming a really accepted approach. And what I'm trying to do actually at the moment is bridge back to the probabilities a little bit more, and that's where the Bayesian thing, which I won't get into, but it does provide a bridge because Bayesian reasoning is all about hypotheses, and a scientific hypothesis is actually a storyline. So you can connect the statistics and the physics through this kind of reasoning, and I think that makes people more comfortable. So you can't just it would be confusing if people started talking about storylines and then they open IPCC and they just get probabilities and they can't connect them. So it's important to bridge them to show how they connect. So you can use some probabilities as a broader context and then use the storylines to really be much more specific. So I think it's really catching on, and I mean I guess I'm trying to build the proper you could call it epistemological foundation for it, which is why I'm also working with philosophers of science to try to make clear that it's a respectable scientific practice. Yeah, but certainly a lot of people really respond to it for sure.
Well, people. If you find yourself in a story, right, you can put yourself in a story, or you can put people you care about in a story, so that it contextualizes it quite a bit. What about where we are all heading with this? I mean, what are some plausible storylines that are making sense to you? You said you're worried about the future. First of all, you seem worried not just on the environmental side. There are these social tipping points. It's hard to study cascades, though, because if you accept that, well, one thing is tipping points, right? They are big events potentially, but cascading effects that cross domains, right, from climate to economics, or climate to social or health impact or local impact, like you said. I mean, clearly there's a lot to be done there to describe these local impacts, and I think we see it now at the climate meeting, right? You have representatives of the global south, and if you are an island these days, that's not a good place to be. You're seeing more extreme climate for one reason or another, and you're trying to get some help with that. But either way, it's complicated. But where are we headed? I mean, are you seeing some sort of consorted direction here? Are we moving in a good direction, bad direction?
Well, I think, I mean, I guess I wouldn't want to give too simple an answer to that. I think that the issues are very linked, though, because I think if we can start to get our act together as a society, and for me that means narrowing rather than widening the gap between rich and poor, and recognizing that we have to help each other ultimately, and not be so polarized. Then I think it's clear that we can deal with climate change. But if we can't get our act together, then we won't deal with climate change. So I think they're actually not really separable things. Or if we do deal with climate change, we'll do it in a way that just exacerbates the gap between rich and poor, and actually isn't necessarily this. Maybe in a broader sense, it's better for humanity. I'm not sure, but I'm more worried about the fact that actually, that we. So I guess for me I mean, I'm not thinking that we'd ever wind up in an 8-degree world, but I could imagine that we wind up in a 4-degree world with huge inequity between rich and poor, and that would just be awful. But I think there is. Let's hope that there can be a transformation, and obviously it's not. It does require changing priorities somehow. But that can happen it begins at the local scale. I know that people are trying to put pressure on, there's various methods, obviously, and ultimately it comes to influencing governments and policies and taking a long-term view. So I guess it seems like a cliche, but the problem is the long term versus short term, isn't it? But that's, I guess, one of the benefits of storylines approaches is that it does help people make sense of their local situation, and then they can begin to see some optimism as well, how they can start to do things in their own environment that will make the environment better for themselves, and get a sense of agency. Because I think that's the sense I get is that one of the problems is that people feel that they don't have any agency.
Related to that, how do you see the notion of growth? What is growth for you?
Well, that's a good question, because everyone says that we need growth, but I was influenced by Schumacher's "Small is Beautiful," another book from the 70s, and Schumacher talks about growth, but it's growth of well-being. It's not GDP. And Schumacher's point is that where we need to grow is we need to grow in education and health and well-being, and we're measuring the wrong indicators. So I think for me that's one of the problems, is that we seem to be measuring growth by things like GDP, and it's very, very clear that GDP is not a good measure of well-being. I mean, many people have shown that. You get gaps between rich and poor. You get a very skewed income distribution. It measures things that aren't actually helping anybody. So growth should be well-being, and there are various measures of that, of course.
You have just listened to another episode of the Futurized podcast with me, Trond Arne Undheim, futurist, scholar, and author. If you are interested in my products or services, feel free to check out futurized.org/store, where you can book a keynote speech, become a sponsor or partner, request a podcast swap, or buy a few of my books, such as Augmented Lean, Health Tech, Future Tech, Pandemic Aftermath, Disruption Games, or Leadership from Below. If you're interested in any or all of my projects, check out my website, trondundheim.com, which has links to other podcasts as well as my public appearances. Thank you. Please share this show with those you care about. To find us on social media is easy. We are Futurized on LinkedIn and YouTube, and Futurized 2 on Instagram and Twitter. See you next time. Futurized, conversations that matter.